So this is the third part in our series, and we're going to have a look at Archimedes' Principle. Now, in the previous series, we looked at analyzing different types of pressures and just laying the groundwork to where we are now. So let's get right into it, and our first step here is to really understand what is Archimedes' Principle. What is it all about, really? And then we're going to get into some worked examples. Now, Archimedes' principle states that if a solid body floats or is submerged in a liquid, then the liquid exerts an upthrust on the body that is equal to gravitational force on the liquid that is displaced by the body. Now, that might sound a little bit confusing, but all it really is talking about is that if a solid body is immersed in a liquid, then the apparent loss of weight is equal to the weight of the liquid that is displaced. And we're going to look at a question that will capture all of what I've just said. So here in this question, we are going to basically apply Archimedes' principle. And for the question, we're told that a body weighs 2.796 newtons, and in this case weight is actually the same as a form of force. That's why the unit is in newtons. Now that's the weight in air, and it's 1.925 newtons when completely immersed in water of density 1000 kilograms per meters cube. Now what we're going to analyze here is the volume of the body to begin with, then the density of the body, and we're looking at the relative density as well. So this will have us referring back to what Archimedes' principle states earlier. And the first thing that we're going to look at is looking at analyzing part A, the volume of the body. And to do this, we're going to first acknowledge or assess what the apparent loss of weight is. And to do that, let's say apparent let's say weight loss, and what that is. So it's 2.760 newtons minus 1.925 newtons. So that's looking at the weight in air versus the weight in the fluid and what the difference really is. So this is going to give us 0.835 newtons. So that is representing the difference in weight between our measurement in air and when it's fully immersed. Now that weight is also the weight of the water that's displaced. So you can look at this formula then. So that's representing the weight. Now, similar to what we did with pressure, where we have density multiplied by gravity multiplied by height, we also have this one here where that's volume multiplied by density and multiplied by gravity. And this is what's actually representing the weight of the displaced water. So if we replace that weight now with the difference that we just calculated, so our 0.835 newtons will be equal to, our unknown in this case is volume. We do know what the density is, it's 1000, and we also know what gravity is, it's 9.81 or 9.8. So this formula then will allow us to calculate what our volume of displaced water is. So therefore, in this case here, the volume is 0.835 divided by our density times gravity, so 9.81 times 1000. So our volume is 8.512, and it's times 10 to the power of 4, and of course it's volume, so we'll use millimeters cubed. So that is representing the volume of the displaced water. So that's part A done. Now part B is us looking at the density of the body. So let's take a look at that. So we do know that density is equal to mass divided by volume. And our mass here in this case has to be converted into our weight. So that's the weight divided by, and we have our formula here. So since we have mass equals weight, then for volume, it's just going to be gravity multiplied by volume. And the reason for that is because if we multiply mass by gravity, then that's going to give us weight. So what we did here was to multiply both our numerator and our denominator by gravity. So therefore, we have gravity times volume in the denominator there. So let's tidy up our equation here now. So our weight is then 2.760 divided by our gravity multiplied by our previously calculated volume, which is 8.512. And this is going to give us a density of 3,305. That's kilograms per meters cubed. So that's representing the density of our body. And the last bit, which is probably the most straightforward bit, is to analyze what our relative density is. So for the relative density, it's just the density that will be divided by the density of water. I'll just write H2O for water. So what we have here then is the density that we calculated previously, which was 3,305, and that's what will be divided by 1,000. So we have a relative density of 3.305. And that will have no unit because the kilograms per meter cube will cancel out each other. So that's our final answer there for relative density. Now we will keep building on this series, so if you got some value from the video, then I would really love if you could give the video a like if you like it, and subscribe to the channel for a lot more content like this. So I will see you in the next video.